nothing can travel faster than this, right? Okay. How about electromagnetic spectrum? Electromagnetic spectrum is actually a collection of all forms of electromagnetic waves. Now, I think in the discussion on thermodynamics, we talked about the radiation that are emitted by all objects. All objects at all temperature emits radiation in the form of electromagnetic waves. Now, electromagnetic spectrum, radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays, are all electromagnetic waves of different wavelength and frequencies. Now, all these range of waves or radiations put together is called electromagnetic spectrum. The wavelengths of these radiations vary from about 1 kilometer for radio waves, but radio waves themselves range from few kilometers to few millimeters. Short waves and long wave radio. Now, so vary from about 1 kilometer for radio waves and a few picometers for very high energy gamma radiations. These gamma radiations are so short they can actually penetrate through you without even knowing. Now, the speed of electromagnetic waves can be expressed in terms of their frequency and wavelength. Well, all forms of waves are described by this equation, C equal to F lambda. So we got actually two equations for speed of electromagnetic waves. One in terms of mu 0 and epsilon naught, the other in terms of the frequency and wavelength. Now here is a rough picture of electromagnetic spectrum. If you start from the left, you got radio waves of wavelength few kilometers, and you go to the right, the wavelength is steadily decreasing, and you come to microwaves. Well, all these are radio waves. Long radio waves to short radio waves. Then you have a range of microwaves. You have radars, infrared, which are heat rays. So the wavelength is steadily decreasing. And look at the visible light. Visible light is a very small part of the electromagnetic spectrum. And how many different types of waves are in the visible region of that? It's over 3,000 different waves. Well, then comes to ultraviolet, we got X-rays, gamma rays, and so on. So the wavelength ranges from, say, 10 to the power of 3 meters to about 10 to the power of -12. That's the one I talked about, a picometer. Now, the frequency of radio waves, say, is about 10 to the power of 6. Now, as the wavelength decreases, the frequency will increase. And the energy, well, a radiation carries energy. The electromagnetic radiations can be considered to be particle in nature, and we call those particles photons, and the energy of the photons are also listed there. The energy steadily increases as the frequency increases. You can see the energy is given in electron volt. An electron volt is the energy acquired by an electron when it is accelerated by just 1 volt. So you can see the energy of a radio wave photon is 10 to the -9 electron volt, 1 billionth of an electron volt, very small energy. While the energy of a gamma ray photon is about 1,000,000 electron volt, a big difference in the energy. So you must have a rough idea on electromagnetic waves, their relative wavelength to frequencies and energy values. visible light consists of over 3,000 different frequencies, and each frequency corresponds to a color. So how many colors are there in our visible light? There are over 3,000 different colors. Well, the perceived colors, very often people talk about 7 colors, the rainbow colors. They are the perceived color, like red, orange, yellow, green, cyan, blue, and violet are actually combinations of many hundreds of wavelengths. Now, for example, red is a combination of wavelength from 625 to 740 nanometer. Now, blue color that we normally see as blue is a combination of wavelength that range from 435 to 500 nanometer. So it's a combination of about 65 different wavelengths. Alright, let's do an example. Find the wavelength for a radio wave of frequency 1000 kilohertz, a radio wave of frequency 100 megahertz. It's a very simple problem, because you know that the speed of all electromagnetic waves is 3 times 10 to the 8 meter per second. And we also know that speed is related to frequency and wavelength as c equal to f lambda. So to find the wavelength, we solve for lambda here. Lambda equal to c over f. So in the first case, it will be c divided by 1000 kilohertz is 10 to the power of 6 hertz, and that is 300 meter, the wavelength of that wave. In the second case, the frequency is 100 megahertz. Well, 100 megahertz is 10 to the power of 8 hertz, and that wave has the length of 3 meter. As the wavelength, as the frequency increases, the wavelength becomes shorter and shorter. Second, what is the frequency of a 1.2 centimeter microwave? Well, again, solve for frequency and use the given values, and that is 1.56 times 10 to the 10 hertz. Next, we will briefly discuss energy and momentum in an electromagnetic wave. These waves carry energy with them. The propagation of electric and magnetic fields results in the propagation of energy. Now, this means that electric and magnetic fields carry energy. Now, the electric energy density U sub E of the electric field E and the magnetic energy density U sub B of the magnetic field B are given by the expressions. We actually discussed them briefly before, if you recall. And these expressions are U sub E, which is the electric field, electric energy density, is 1/2 epsilon naught E squared, and a similar expression for magnetic energy, U sub B, that is the magnetic energy density, is B squared divided by 2 mu 0. I think we discussed these in our last lesson. Now, since E equal to CB, remember that? We can actually modify these equations. Suppose we replace our B by E divided by C here. Can you do that? Replace this B by E divided by C. What will that become? UB become E squared epsilon naught mu 0 over 2 mu 0. Is that right? Well, did you see how that was obtained? Well, we replaced B by E over C, and our C is 1 over square root mu 0 epsilon naught. I want you to do that on your own and see whether you come to this. You can see UB therefore also is 1/2 E0 epsilon naught E squared. That means if you replace B using E equal to CB by E over C, you will see UE and UB really have the same magnitude. So the energy density is the same for both E and B. That's what we just showed. The total energy density, therefore, of the electromagnetic wave U is the sum of the two, UE plus UB. That is 1/2 epsilon naught E squared plus 1/2 epsilon naught E squared is epsilon naught E squared. And you can write this also as B squared over mu 0. Epsilon naught E squared and B squared over mu 0 are both the same, using the relation E equal to C times B. And of course C equal to square root of mu 0 times epsilon naught. Okay. Now the average energy density can be obtained by replacing E and B by their RMS values. So if this is the energy density for an electromagnetic wave, EB divided by mu 0 C, what is the average energy density? It will be E RMS times B RMS over mu 0 C. Now this average energy is a measure of the momentum P carried by the wave per unit time per unit area. Now that's an important concept. Alright, so the average energy E RMS B RMS over mu 0 C. Now what is the meaning of intensity of a radiation? We talked about in connection with our discussion on waves, intensity. Now, if there is a radiation that is emitted, for example, I'm standing in front of a projector and the light that is falling on me is from the lamp of the projector. That's why you see my shadow on the board. Now, what is the measure of the intensity of that radiation? Well, in order to define the intensity at a particular point, what we do is we keep a unit area where we want to find the intensity. It is the amount of power crossing at right angles to a unit area is what we call intensity. So intensity is a measure of the power crossing unit area at that particular place. Now if I move this unit area away, the amount of power crossing that unit area will be now less. That means as you move away from the source, the intensity will become less and less. Alright, so the intensity I of the wave is defined as the product of wave speed and the average energy density. Well, having known what intensity is, we can make use of that definition. In other words, intensity I is the product of the wave speed C and the average energy density. So I can now write it as C times the average energy density is E RMS B RMS divided by mu 0 C, and that will be E RMS B RMS divided by mu 0 because the C's will disappear. Now the intensity divided by C is the force per unit area. What is force per unit area called? Force per unit area is called the pressure, and therefore the radiation pressure, whenever a radiation falls on a surface, there's a radiation pressure. And how do you calculate the radiation pressure? It is the intensity divided by C. I divided by C is radiation pressure. So P sub R, the radiation pressure, is intensity I divided by C, the wave speed, and that is equal to U is E RMS B RMS divided